Last year I must have forgot to hit the record button when we did this lesson. So it's called areas between curves. We've already been dealing with areas now for a while. Every problem we have done up until this point would have read like that first one there, where it says find the area between the curve x squared plus 1 and then the x-axis between 0 and 4. So we've done this in different ways. The first way we would have talked about this is I would have had you graph it. We would have gone from 0 to 4. I would have asked you to approximate this area. And the first way that we would have approximated it would have been with rectangles. So we would have drawn in some variation of rectangles, left endpoint, right endpoint, so on and so forth. All right, that's an approximation for how much area is in there. We eventually did trapezoids as well. Trapezoids will also approximate the area. And then ultimately, long term, if it's a basic graph like this, we set up an integral saying that we would integrate from 0 to 4. The height of all of the rectangles that we were in here, even though we're smashing an infinite number of them in there, is just that x squared plus a 1. That's the height. And then our base is going to be our dx. All right. So every time we've done this, we've really just had one curve. If you now look at the title of the section, this is just area between, and you're going to see the word curves, which implies there's more than just this one curve in the x-axis. It would be multiple curves or multiple functions. All right. So what that sort of now entails, the reason whenever we've done one of these, our height has always just been this function value, like y equals x squared plus 4, is because if I took, let's say this is the x value of 1, if I just took that x value of 1 and plug it in here, and I get the point 1 comma 5, do we all agree that the height of this rectangle would be 5? Yeah, the reason because that is the case is because isn't the bottom of this rectangle, every single problem we've done so far, hasn't that always been the x-axis, which is a y value of 0? So the difference between this y value on the curve and the y value of the bottom of our rectangle would always just ultimately be that y coordinate. However, if instead of the x-axis, let's say I told you to find the area between now this parabola and then this horizontal line y equals a negative 1, so that now our area extends to down here, would the height of those rectangles all now simply be whatever the y coordinate is on that curve? No, they would all increase by how much? Yeah, they all would have gone 1 unit lower. So the y value by itself of the curve would no longer simply be the y or the height of our integral. All right, we agree with that. So that's what this is now going to be getting at. We're not always going to be dealing with the x-axis. It's just going to be in between multiple curves. Okay. So with that setup, I'll kind of define this here in a minute. I kind of like you to see the first problem, then it's easier to describe what's going on there. So go down to number 1. You'll have a calculator on Friday, so if you need to use your calculator to graph it, feel free. The first handful we should probably be able to do without. So if I ask you to find the area between this curve and this line, you certainly do want to sketch it. So if you need your calculator to do that, you're more than welcome to, but this is one that we should be able to sketch. It's a parabola. The negative means we're opening downwards. The vertex is 0, 3. So up here it's 0, 3. We should be able to sketch in a parabola that opens downwards. Then this is a line and slope intercept form. So our y-intercept is going to be a 1 for this line. And then we have a slope of a negative 1 right here. So if we then sketch in a line with a slope of negative 1 through the y-axis at 1, that's what our graph would look like. Don't do this to yours, but let's say I don't have this. So I'm going to cross out where this says x equals 0 to x equals 2. A lot of the problems you're going to do, probably the majority of them, you just have to look at your figure and find where is the completely enclosed region. So if I didn't have that there, the completely enclosed region, we would hopefully look at this and identify that this would be the area that's enclosed by those two graphs. Okay. However, I do give you an interval. I only want it from 0 to 2. So as we look at this now, we now need to be a little more careful. Clearly, we don't want this over here. This isn't 0, but we would definitely start here because this is 0. And then we would need to go over to 2. We don't really know where 2 is at yet. We'd want to investigate a little bit. So we kind of want to know what is this intersection point right here. The way we're going to do that is just old school. You can take those two equations, set them equal to each other, and then those should give us the two values where those graphs intersect. quadratic equation, we want to set that equal to 0. So I'm going to move these left terms over to the right-hand side so that squared term becomes positive. So I'm going to have a 0 on the left, and then we'll put this in the right order. Positive x squared, negative x. I would have subtracted the 3 over, so I would get a negative 2. Simple little guy to factor here, so we continue to solve this by factoring. And what we find is our first intersection point would have been a negative 1. So this point right here is a negative 1. We're not concerned about that only because it's not within the interval that I gave you. If I didn't give you that, then that's important. The other x coordinate is 2. So what we found is where that parabola and line intersect is in fact 2. So the area that we are looking at starts at 0, goes to 2, and we just found the intersection point is 2. So this is the region that we are finding. Like I kind of talked a little bit about at the top of the paper, this is still very much dealing with the idea that we have an infinite number of little rectangles in here. I'm just going to kind of sketch a couple of them in so we know where the setup comes from. But we jam all these rectangles in there. We want to add them all up. The integral is what does the sum. Again, that's what we talked about. It's kind of an S shape to still be synonymous with the idea of a sum. If I now ask you to do your height times your base for these rectangles, wouldn't our height right here simply be the difference between the y value on the top of the rectangle and the y value on the bottom of the rectangle? So what we really want to be able to do is find the difference between the y value of the parabola and the y value of the line. So what these always will boil down to, and this is kind of where this formula comes from, is whatever function is on top minus whatever function is on the bottom. That difference gives you the rectangle in between. That would be the height of each rectangle. Okay, you follow that? So for this particular problem, if you look at these red rectangles that I have drawn in here, the top of each of these is the parabola. So I'm going to put the parabola in first, 3 minus x squared. And then I'm going to use some parentheses here. I might have to add a little space. And then I want to subtract whatever is on the bottom, which is the line 1 minus an x. That is the height of every single rectangle. Our base, if we were still dealing with Riemann sums, would have been the little delta x, and we'd have to do, 4 rectangles, all that good stuff, and multiply by half or a quarter. But since it's a definite integral, it's just they're infinitely small as we jam them all in there. So it's just our dx, our change in x. If I ask you where this yellow region starts at, what x value does the yellow region start at? 0. And then this is all the rectangles starting at 0 until that region ends at the x value of what? 2. So this is our setup. Okay. You'll have a calculator in your hand. We do long-term want to be able to do these without a calculator sometimes, depending on how hard they are. Some can and cannot be done with a calculator. I do want you to practice these first handful of plugging them in so we don't fumble around too much on Friday. You can plug this in right now, just like this. Some people prefer to simplify a little bit. It's really up to you, so I don't really care. So you may want to distribute, get the negative 1 plus an x, plug that one in. If you really want to completely simplify, you can do negative x squared plus x plus 2. All 3 of these versions should spit out the same exact answer. It's just how much do you want to simplify before you just plug it in. Some people won't simplify at all. That's fine. Have a thought process, have a method, so when we get to these on Friday, you just don't plug it in wrong. All right, throw that in there. Make sure we get this. So it's just a Math 9. A lot of you reviewed that a little bit on that assignment here the last few days. And is anybody confident in what they got? Good. 10/3. So 10/3, 3 1/3. If you give me decimals, you got to stick to that 3 decimal rule. Make sure you put 3 of the decimals in there. But that should be the area in that region. Okay. If you don't get it, check your parentheses. If you use this method, make sure you distributed, things like that. All right. Any issues with that? Good. All right. Number 2, I think, is an easier version. And that should have hopefully been pretty nice, even as the first problem of these. This one, again, you could probably sketch this without your calculator. 2 minus x squared is another parabola that opens downwards. Vertex at 0, 2. The line y equals a negative x goes through the origin. I should extend this a little more. It has a slope of a negative 1. So rough sketch, that should be what our graphs look like. Compare, contrast this one to number 1. They look very similar for a reason. I kind of want them to look similar. The difference is now in number 1, I told you the interval to be concerned about. We only wanted to go from 0 to 2. You don't have that condition in number 2. So it really is just looking at the figure, understanding what region is completely enclosed, that if you were there, you could not get out. And then that's the area we're looking for. So in this case, we are looking for this region right here. This is the only region completely enclosed by those two graphs. All goes back to rectangles, like we said in the first couple. So if I draw in a handful of little rectangles in here, it doesn't matter where I draw it in. The height of every rectangle in here, no matter where I've drawn it in, should have been the difference between the top curve and the bottom curve. The parabola is on top of all of them, and the line is on the bottom of all of these. So it's still an integral. The integral still finds the sum of all of our rectangles. Each rectangle has a height defined by the difference in the parabola, which is on top, and the line, which is on the bottom. That's all of their heights. We're multiplying by the base, which is that infinitesimally small change in x, the dx. What we do need that we're missing, that we got to do a little bit of work for, we need to know what our limits are right here. And that would simply be where this area starts. So we need to know what is this intersection point right here. And then the area ends right here. So we would need to know what is that intersection point right there. Once we know those are your two limits. Just like we did in the previous one, we can figure those out by just setting those two equations equal. Get everything set equal to 0. Make sure that x squared is positive just to make sure it stays nice and easy. And then that should look very similar because it's the same quadratic equation we got in the previous one. So those intersection points then become, when we factor it, x minus 2x plus 1. So the first intersection point's a negative 1. So that is where this region will start. The second one is the x value of 2. So that is where that area stops, which means those are your limits. We start at negative 1, finish up at 2. You have a calculator in your hand, so whatever version of this you want to plug in, but you could plug it in just like this, and it should give you the answer. All right, so people have already plugged it in. What does that give us?
Nico, I haven't plugged it in. Sorry, Smith.
What do we get? Good. That should give you 4.5 or 9/2, whichever version you prefer. If you're not getting it, try it again. Still can't get it, I can kind of look at it. Just keep your order. This one's not too bad. Some of these are going to get ugly over the course of this next week. This is going to be a lot of math 9s in your future. Okay, so we want to be pretty efficient with that. Okay, Sebastian, good.
Yeah, my thing just keeps going though.
Just keeps going.
Turn it off. It's your Y with those also. They're all smashed in there. So when I go here, I'll send out. I don't think that moves.
No.
You just do it the right way. Oh,
All right. Everybody else good with that then? Yeah.
So if you did both, like if you graph both and then did like the calc trace thing, why is that one like a different answer?
because it doesn't understand what the bottom curve is. So if you only try to shade underneath one of them, it's not going to keep that line on the bottom. It's only going to do the parabola over the x-intercepts or whatever the interval is going to be. Like when you shade it shades it in, right? Does that that diagonal line keep you bordered on the bottom? No, so that's our problem. Okay. All right, so hopefully those are pretty nice. Number 3, not that this is hard, but about as hard as this would get, as involved as this would get. Similar looking graph at the beginning. I kind of want all 3 of these to be similar. So 4 minus x squared, another parabola, opening downwards. Our vertex is now just up here at 4. Y equals a negative x plus 2 is a y-intercept of 2 and a slope of negative 1. So that should kind of look like this. We now have dealt with ones where I've given you an interval and I don't give you an interval. I am giving you an interval in this one. Again, if that's not there, then this is pretty easy to identify. You'd be looking for this region right here. And you could still very well be looking for that region. We just don't know yet until we know what this intersection point is and what this intersection point is, and then how those relate to the x values that I told you to say in between. So the intersection points in this, pretty critical. We know what those are right from the beginning. So we're going to find those first. And then I didn't necessarily mean for all of them to end up being the exact same, but for the 3rd time in a row, that's our quadratic equation. So that should be very easy to factor. And what we find then is the first intersection point is the negative 1. The second intersection point is 2. So that's this guy right here. If we then revisit the limits that we are concerned about, then we see we have a small problem, a little problem. This area starts at a negative 1, but I needed you to start at the x value of a negative 2. So what that then means is I need to go over here to the x value of a negative 2, and we kind of have this imaginary vertical line then that's acting as a left-hand bound. So if we have to be in between the 2 graphs and we have that left-hand bound, what that gives us is it's kind of like a triangle. It's not really a triangle, but it's similar, triangular. We also now have this region. So that starts at a negative 2, but we needed to go all the way over to 3. We found the intersection point here to be a 2, but I needed to go all the way over to 3. So similar to what we did on the left-hand side, over here at the x value of 3, we now have this kind of imaginary vertical line that borders us to the right. And we would also now, in between the 2 graphs, give you this. So what we would then see is we have 1 region here, 2 regions here, and a 3rd region right there. That's also why we definitely want a calculator, so this doesn't take us 15 minutes to go through all this work. But because we have 3 different regions, as we go to set this up, so hopefully I have enough room here. I'm going to move this down a little bit more. So as I go to set up my integral, the left-hand side, we're going to work left to right. That first one starts at a negative 2. And when I start at a negative 2, what's on top, the parabola or the line? The line. So initially, I'm going to put the line on top, and I'm going to subtract the bottom, which is the parabola. But this relationship is only true from the negative 2 until what x value? Negative 1. So this integral here, when we punch that into our calculator, will give us the area of number 1. Plus. When I do region number 2, that one now starts at the x value of a negative 1. And oops, that's not a negative 1. And starting at the x value of a negative 1, notice how now the parabola is on top, the line is on the bottom. So this integral will start with the parabola first, minus the line. But this relationship is only true until we get to the x value of 2, and then they flip again. So that one goes from a negative 1 to 2. Plus, and then finally, this third one, hopefully usually by now people are understanding sort of how to set this up. That one would start at 2, go to 3, And then between 2 and 3, the line has jumped back on top. And the parabola is on the bottom. From here, again, it's really up to you how you want to approach it. You really can do math 9, plug this in, and then do a plus sign, hit another math 9 and plug that in. You can do it all at once if you want. Some people do. I don't really care. Some people will do this first one, write the answer down. They'll do the second one, hit enter, write the answer down. Third one, write the answer down, add them all up. But again, that's kind of why I want you to try the first handful so we have a strategy so you're not doing this for the first time on Friday. Whatever you think you would do, try it. See what we get. And then if anybody's confident in their calculator usage, let me know. Because there's a lot to plug in here. So you have to have, if you have time on Friday, I'd plug it in twice, something this ugly, just to make sure we didn't make a little error. All right, anybody confidence here? Didn't screw anything up. What'd you get?
49 over 6.
Good. Yeah, should be 49 over 6. All right. Doing it all at once, it gets a little tricky because you can't see it all. So it's hard to kind of double check it before you have to hit enter. But it's really up to you how you're going to plug those in. All right. Are more people getting this? Now we're plugging it in. Okay. Yeah, that's fine. Yeah, that would. What is that? 8 and 1 6. Yeah, so 8.16 repeating. All right, that's about as involved as they get. There's little things here coming up, but yeah, 3 integrals having to do all that. I mean, overall, this is not too bad. All right, go to number 4. Another one that we could probably do without our calculator in terms of sketching it. We just have 2 lines. Y equals x minus a2. Actually, let me move this up just a little bit here. So a y-intercept of a -2 with the slope of 1. So like so. And then y equals 2x should go through the origin, and it would have a steeper slope of 2x. So it should look kind of like this. I didn't draw that particularly well for what I want you to see, but there's your graph. Notice how there is no enclosed region right now, right? There's no like completely enclosed space. So we definitely need some intervals to cover. And I want you to go from a -4 to 0. So -4 to 0, it would be nice if this intersection point right here was a -4, because if it was, then we know where 0 is at. We would just be dealing with this little triangle. But again, we don't know that. So we want to kind of identify that right off the bat. So we're going to figure out where these intersection points are. So set them equal, subtract that x over, and we find pretty quickly that they actually intersect here at the x value of a -2. Since we need to start at -4, similar to the last one we just did, I need to move over to a -4, and then we have this as our left-hand bound. So we just have a second triangle right here. Now we have 2 regions. We'll need 2 integrals. So when we go to set this up, I'll call this region 1. This will be region 2. Region 1 starts at the -4. And starting at -4, this line here is on top. This is the one that has a y-intercept of the -2. So that's the x minus 2 on top. The bottom line is 2x. And then that is true until we reach the x value of a -2. So that's our upper limit. Plus -2. At -2, those flip-flop. So now twice x goes on top. The line x minus 2 is the bottom. And then that is the case until we finish off at the x value of 0. These are nice. These are hard to mess up too. I would trust we could get both of those. Those both end up being 2. So all together then we get 4. All right, real quick, do number 5. 6, 7, and 8 both have little things here that we want to be careful of. 5 would be about as easy as it gets. So now that we're 4 in, you've seen some of these. 5 would hopefully be one you can look at, and in about 60 seconds, have it set up and have that answer. So do 5 real quick. See what we get.
Keep that one, sir. Yeah, it's your views.
Should be a nice number also. One we probably don't really need to use our calculator to graph. Simple horizontal line, parabola. No interval was given, so you're just looking for this region right here. All right, when we go to set this up, Megan, what were our limits? Good. So they would have intersected here at -3, over here at a +3 when we set them equal. All right, honey, and what's on top? Good. And then minus the bottom, which is good. And then our base is the change in x. And then Nico, what's this give us?
36.
Good. And then you should just get 36. All right. So that's kind of basic. One top curve, one bottom curve, no interval, as nice as they could come. All right. All right. Now, the next ones all have little things to just be a little bit careful of. 6, I could ask you with or without your calculator. We're going to do this without our calculus. I think it's a little bit quicker, and it should allow us to get all 3 of them done. So we're going to look for the area between sine and cosine from 0 to pi over 2. So on a graph, just draw in a little xy plane, and we're just going to go from 0 to pi over 2. We're going to do the sine curve first. So what is the sine of 0? 0. So we're going to go through the origin with the sine curve. What is the sine of pi over 2? 1. And then just kind of know what the sine curve looks like. It's obviously a wave graph. So sine of x in this interval should kind of look like that. When we graph cosine of x, what's the cosine of 0? 1. So that one goes through 1. And what's the cosine of pi over 2? 0. So kind of sketch in what cosine looks like. It looks like this. We then have to stop at pi over 2. So we again have this vertical line here that stops us from going any further. And for the first time, you probably got to think a little bit about what we're really looking for. So look at that, process it. We now have 3 regions to be concerned about. What are we looking for? Shade in the ones you think we are actually trying to find. Which one is the answer? All right. It's the region between sine of x and cosine of x. It's got to be enclosed by those 2. What are we looking for? 1, 2, 3, what?
1, 3.
Good. It should be 1 and 3. It doesn't say the x-axis, so really you can't, while we use the x-axis to graph, you really can pretend that that's not even there unless it's said it's bounded by the x-axis. And then it's clearer if the x-axis isn't there. Now, the x-axis is there for the sake of graphing it, but that would have been an unbounded region down here. So 1 and 3 are what we're looking for. So 2 integrals. The first integral definitely starts at 0 for region number 1 right here. Within region number 1, which curve's on top? Cosine x. And then sine of x would then have to be on the bottom. That's not the case the entire time, though. They're going to flip-flop right here. What does this have to be? Good. It's got to be pi over 4. You can try to set them equal to each other like we've been doing, and you do want to do that, I suppose. But the only way to really solve this is understanding on the unit circle between 0 and pi over 2, so this region right here, the only place sine and cosine are equivalent to each other is at the angle pi over 4. So that intersection point must be pi over 4. That gives us area region number 1. Now, this you should know. Are these going to have the same values? Yeah, same interval, same curve. So you could just double that. Although, why do I have a 0 there? Or not a 0. This should be 0 to pi over 4. But we'll go ahead and set this up since we're just kind of starting with this today. The second one, then, this third region should start at pi over 4, finish at pi over 2, and then they flip-flopped. The sine curve now is on the top. The cosine curve is on the bottom. Okay. Now, make sure you're in radians. This is the first one with the trig function. I'm going to start giving you some of these so we can make sure we get through these last two. That's the overall answer, 0.828. You could just do one of them and double it. If you don't get that, make sure you're in radians. Friday, make sure you're in radians. So if I give you a trig one, we're going to get the right answer. All right. 7. So here's what you're kind of concluding right now, and 7 will contradict this. That's why I give you this. When we've had two regions, like we just did in number 6, you had two integrals. When I've had one region, we've had one integral. If we went all the way back to number 3, we had 3 regions, and we had 1, 2, 3 integrals. Okay. When we go to number 7, I want you to find the area of that shaded region. And I actually forgot to label one of these, or at least give it to you labeled. So this parabola right here, label the parabola. That is x squared over 4. It's also the first time I've given you 3 different curves. And we have that region right there that we are looking for. So we're going to set up an integral because we're obviously again adding up these rectangles. And when I start drawing these rectangles in starting at 0, so my lower limit is definitely a 0. So any rectangle I were to draw in starting at 0, so any of these rectangles here, this line y equals x is on the top of any rectangle within that region. So the top curve / function is x. The bottom of all of these rectangles is this parabola, x squared over 4. So right now we're saying when we start at 0, the line x is on top, the parabola is on the bottom. This area ends over here at 2. If I put 2 right here, is this relationship true the entire time? No, that is only true starting at the 0 until we reach what x value? 1. So even though there's only one area, this still requires 2 integrals because that top curve changes. So right at that x value of 1 here, when we do the integral that we now currently have set up, it's going to give us this region. But I would now need to make sure that I do plus and then go to the second one. Yeah, Sebastian.
How do you find the parabola? Like, how do you define it just by using the graph?
How do you find what?
How do you find it x squared over 4?
I knew it because I put it in the computer, and I just forgot to label it on the paper. So it should have been labeled.
So when would you give it?
Yes. Yeah. Okay, the second one then would start at 1. And starting at 1, what is now the top curve? Yeah, y equals 1. What's the bottom curve in that region? Yeah, the parabola is still on the bottom. And then that just goes from 1 to 2. I don't remember that one. We didn't punch that one in 4th period for me to see it. But again, now it's just a matter of plugging it into your calculator. So just be careful. Don't make any little errors there. But that should be your answer. Okay. Anybody have that handy? Anybody looking at it? What'd you get?
5, 6.
What is it?
5, 6.
5.6?
Yeah, which is.
Do we all get that?
6.8.
Okay. All right, we got a few head nods to that too, so it sounds good to me. All right, 5.6. All right, last one. This one you do need to graph on your calculator. Even though you should be able to sketch this, you won't be able to answer this question without it being on your calculator. So go ahead and graph those two. All right. Yeah, if you didn't have the calculator and I told you to sketch that, you should be able to sketch that. We know that's a parabola opening downward, vertex 0, 1. We'd be able to just sketch in a general sine curve. So that's not the reason we need our calculator. But when we graph that, I don't give you an interval to be concerned about. So you're really just looking to see where we're completely enclosed, and that would be this space right here. When we look at this, no matter where I draw a rectangle in here, we can see that the parabola is always on top. The sine curve is always on the bottom. So nothing tricky in regards to that like the previous question. We can go ahead and set up our integral and know sine of x is always on top. No, it's not. Parabola is always on top. And the sine of x is always on the bottom. All right, so pretty straightforward right now. Nothing tricky here. We now need our limit. So we now need to figure out, where does this area start? Where does this area end? Same as we've been doing, we would want to set those two equations equal to each other and try to solve that. When we see this, we would hopefully realize that this would keep you busy for a very long time trying to solve this by hand. All right, so this is why the calculator is now needed. So to figure this out, isn't on a graph the solution to two curves, isn't that simply their intersection point? So you'll certainly be doing a lot of intersections in this chapter. So we have done this periodically. You'll do it a lot this chapter. It's underneath the calc option, so above the trace key. So second calc. It's number 5. There are multiple intersections. So just make sure you're close to the one that you're looking for. I'm going to find the lower limit first. So I'm going to mosey on over to that one. First curve, hit enter. It automatically jumps you to the second curve. Hit enter again. And then guess. This should be your intersection point. Now, we want all of these decimals. We don't want to use a rounded answer in our answer. We need to be accurate to 3. I tried it earlier today and it didn't work good. So I got to refresh my memory how to get all of those values. But going to that 6th decimal should be good. So we're going to put all of those decimals. Do not round that off. So negative 1.4. No, I forgot already. 09264? 624. And then you need to do the same thing for this one. So second calc intersect. And now just make sure your little guy gets close to the second intersection point. And we should get this, 0.6367327. All right. From there, it's not hard. Just be careful. It's a lot of plugging into the calculator, a lot of decimals in there. Anybody have that one already? Yeah.
Which one?
3 decimals.
1.670.
1.6 what?
70.
That sounds familiar. Yeah. All right. Are we getting that? Good. So it really just boils down to top minus bottom. And if that ever flip-flops, then we may need to set up multiple intervals. Okay? All right. Right on time. Perfect timing there. All right. That's all we got. So,
Mr. Tagline,
yes, sir.